That'll do. Right, morning. After a slightly disorganised start, there we are. So I'm Paul Evans, Leonard. Sorry, let me get it start. So I do, many people probably know who I am. I do a lot of I also do a lot of electronic stuff, which I haven't talked about at LPW before. So I thought, given that this is the Internet of Things, and things are very electronic, I thought this would be a good opportunity to start. So I'm going to do a talk today, if I can get it to advance. Yeah. So there'll be three main parts to this talk. So I'm going to be talking about the main subject, which is a thing called the bus pirate. So I'll tell you all about what that is, what it does. Talking about how to use it from Perl, because I have to get some Perl in the talk somewhere, otherwise it would be very exciting for everyone. And finally, some things that I've done with it. So three quite separate subjects. Hopefully, if anyone gets bored with one bit, they will not be too bored with the rest of it. So there should be something for everyone there. So, on to section 1. So a thing called a bus pirate. If anyone knows what this is. It's a piece of hardware. I've actually got one. I had more than 30 seconds worth of preparation. I've got it out. The thing looks like this. It's made by, I don't know if they're a company, a group, internet people. They're called Dangerous Prototypes, not to be confused with the totally different people called Dangerous Things. The Dangerous Things people make things that are actually dangerous. Dangerous Prototypes just do fancy bits of hardware. And their group say that our goal is to release a new open source hardware project every month. So they do open source hardware, which is an exciting concept. So what they say about the Bus Pirate is that the Bus Pirate is an open source hacker multi-tool that talks to electronic stuff. Vague. There, I will explain what that all means. Written designed by a guy called Ian Masnet, which says on the tip. So, what is the Bus Pirate? It looks like this. This is the actual thing. There's a photo of it, slightly larger. It has this USB port on one side. It has this socket header on this side so that you can connect your computer to one side and your electronic device on the other side, and you can talk to your fancy electronic devices. Got these little LEDs at the top just to tell you what's going on. So, really, what it is all about is about putting these I/O pins onto a computer so that you can talk to fancy little bits of electronic kit. So primarily it's got these little general purpose I/O pins. It's got one pin that does analog input, so you can read analog sensors, light sensors, temperature things, stuff like that. But it's not really the point of it. That's just sort of like, well, what are we here with that? It's also got some power pins on there so that you can actually power up the device just because it's nice and handy. That's useful. So, sort of logically, it kind of looks like this with the USB and that I/O pins. Very similar to that project. So, primarily, it's designed as a thing. So you connect to a USB. It emulates a serial port, so it just looks like a normal serial port. With the FTDI chip, which I don't know if anyone's been looking at the news lately. FTDI, the company that makes it, were having a problem with a lot of cheap clones being made of their chips, and they didn't like this. So they put out a new version of the Windows driver that relied on a very obscure silicon bug in all of the clones and bricked all of the clones. And this upset a lot of people, made them very unhappy, because a lot of the end users have these chips and they don't know if they're a clone. And the particular one on my device, I do not know as if it is a clone. Therefore, I will not plug this into a Windows machine anymore. So they screwed themselves over a bit on that. And now everybody is doing a mass exodus onto the various other companies that make USB serial chips, because the other companies don't do that. So if anyone's thinking of doing it, please have a look at anyone else other than FTDI, because they are silly. So yeah, and as a serial port, it's intended to be used by a human on a text console, because you can very easily just plug it into your computer, connect your random little electronic device, and you can start typing at it and start fiddling with the electronic chip, like literally in a minute. It also does have this binary I/O mode, which is useful for writing scripts for, and that's ultimately what I will be going on to that in a minute. But we'll just see. So this is a little screen capture of me actually just talking to it. So you plug it in and you get this prompt. It says hi Z. It's in no mode in particular at the beginning. You press M and use the menu of all the modes, so you can switch it into mode, and then you can start actually talking to the chip. So you type all these little commands in here, like this little square brackets, and you say, send these numbers out to the SPI port, and it goes, yeah, okay, I'll do that. And it sends out the thing. So maybe if you had some sort of LCD panel attached to it, that there might be a command to say, write this text on the screen, or whatever. All of a sudden you have this LCD panel that says the word hello. It's excessively exciting. Because suddenly, literally a minute, you have managed to attach some little electronic device to your laptop and made it work. It's very cool. But it's a lot of manual typing, and it starts to get really annoying when you're trying to drive slightly more complex chips that have lots of subtle behavior on them. So I went in and did this Perl module to do it instead. So as a brief aside into the various things that it can actually talk to, it's called a bus pilot. The intention being it talks to different kinds of electronic buses. Now, what a bus means is sort of one or more electronic cables that are all connected together between multiple devices so that you can talk to two or more things. So, obviously, the first thing it's got is this sort of dumb general purpose I/O, something called bit banging, where you literally just have 4 or 5 pins, and you can decide these ones are high, these ones are low, and you can shuffle them around. It's very low level, very manual, very, very slow to do anything interesting, but generally pretty universal because you're in full control of the pins. You can live your life, you can talk to crazy weird hardware devices that are very weird and silly. But it's not very useful because almost all of the chips that you'll buy to talk, sort of radio modules or LCD controllers or whatever, will be talking some sort of slightly higher level electronic protocol. Primarily, there are the two main ones called SPI and I2C. I will go into. The thing will also act as a serial port, which is of dubious use given that you connect it through serial anyway. So you sort of have a USB attached serial machine that can do many things, including be a serial port. So I don't quite know why they put that on, but sometimes it's useful. The thing itself will also talk a number of other protocols, JTAG, which is a sort of, it's more of a hardware debugging protocol with a lot of more fancy microcontrollers, CPUs and things will talk so that you can do very strange debugging things with them. That's quite universal and powerful. I'm not going to get into that one. For some reason they implemented PS2 on it, so you can read PS2 keyboard. I don't really know why. It also talks the Dallas one-wire protocol, which Dallas made a lot of interesting sensors, like temperature sensors and magnetic sensors, that all sit on this one-wire bus, which is quite useful at that. And because it's all open hardware, open firmware, open everything, people have written custom firmware to support all kinds of other crazy things, and there's a lot of those on the website that talk these very strange things. But primarily the thing talks either SPI, which stands for Serial Peripheral Interface, which is this wonderful generic term that tells you nothing at all about what it actually does, like most things. It's a thing called, it's a synchronous serial protocol. And I talk a lot about asynchronous code. In hardware terms, synchronous and asynchronous mean something completely different to how we might consider them in programming terms. What synchronous means in this case is that you have a clock pin that sends the timing information with everything else, so that everyone else doesn't need to have accurate timing. They pull the clock off the wire. I'll show you that fast in a minute. SPI is a master-slave protocol, so you have one device that is properly in charge of everybody else, and everyone else just has to shut up and listen. So that's typically the bus pirate itself is going to be the master, and you use that to talk to whatever the hardware devices. It's primarily got 4 wires to it, which is kind of a lie because it's a bus. So you actually have 3 3 shared wires for all of the devices, and you have one extra wire per device that you want to talk to. But the bus bar is really intended for talking, for sort of playing around with. You've bought some fancy new chip, you want to use it in a circuit. So you just want to play around with it. So typically you only actually connect one thing to the bus bar at once. So the bus bar itself will only actually support one device. And the names of the pins on the bus bar itself are taken basically from SPI, because that's the primary thing they're really intending you to use the bus bar with. So these pins have these wonderfully amusing names from MOSI and MISO, and nobody ever gets those confused, really honest. These stand for master out, slave in, and master in, slave out, to sort of remind you which direction they're supposed to be going. Because what they're thinking with this is, if you just say data in, data out, then you have to remember to cross them over from one device to the other. So obviously the output from one is the input to the other. Whereas what they're thinking here is to just match the names to everything. And this is the master out, it's also the slave in, and so everyone's all fine. And that mostly works up until you get devices that want to be a slave or a master. You have to think, hang on, which way around is this? Do I have to swap them? It doesn't work so well in practice. We have these 4 pins. 3 of them are outputs from the master material into the chip, and one of them is the reply from the chip. So on the wire it actually looks like this. You don't particularly have to understand all of the detail in here, but I spent ages drawing this pretty diagram, so I'm going to explain it anyway. So as I said, we have it's called a synchronous protocol. So we have this clock line, and so what we're saying is we set the SS line, the slave select line. We say, well, I'm talking to you now. And then the master sends out these 8 pulses on the clock, and each one lines up with a bit that we're going to send out. So after 8 clocks here, we've sent an entire byte's worth of data, which happens to be this number here, 47. Right. So let's byte it out. And then maybe we'll shut up now, and we'll just pulse the clock line again, and we will see if the slave says anything. That is, the slave said B6, 4E, some reading these with arbitrary numbers I picked up. And so this is a sort of a kind of typical example of something that might happen over an SPI bus. So the master here is always in control of the clock. The master here is always outputting something on MOSI, and if it's got nothing to say, it usually just says 0. Because half the time, you're wanting to read something from a device. So you still have to send the clock anyway, and just hope that it said something on return. So it's sort of a full duplex thing, and you can send output and receive input at the same time. It's very fast. But you also have to be talking in order to receive something. If the slave has something it wants to say, they have to just shut up and wait until somebody asks it, do you have any input to say? Which is a bit annoying. As opposed to the other kind of bus that it will talk from Perls to FC, which is another wonderfully generic acronym that tells you nothing about what it's called. It's called Inter-Integrated Circuit, which was a name invented by Philips, and then they trademarked it and stuck all kinds of restrictions on the spec that implements it. So pretty much everybody actually calls it TWI, two-wire interface, because they make a thing that's really, really, really similar to I2C, but they don't have to pay Philips this small amount of money to actually name it that. So in practice, these terms all sort of get confused together. Occasionally, sometimes, especially sort of cheap Chinese manufacturers, will make an SPI thing, which nominally has 3 wires in it, and they will call it 3-wire interface, or TWI. Ever confuse anybody? It's a synchronous serial thing. It's again master-slave-ish. It's only got 2 wires, which was part of the reason they built it. I think they first invented it for TVs, because they started building these fancy TVs with digital pins on them, like digital buttons on the front and LEDs and all fancy stuff. And they got bored of having to wire up so many wires all the way through the circuit boards. And they thought, wouldn't it be great if we could just put, maybe 1 or 2 wires between everything and put them on this sort of bus and have them talk to each other. So they invented this for all of their TVs. And then they decided, actually, this is a nice standard, everyone should do this. So they sort of published it. A lot of people do that now. As compared to SPI, In SPI, you send one wire per chip that you're going to talk to. So the master can say, you, and you just hit that one slave line. So all of the protocol is very simple. In I2C, the whole thing is a shared bus, and every device has built into it an address, an idea of what number it is, which makes things both simpler and more complicated. It's simpler because all you have is two wires that are shared everywhere. It's more complicated because each device has its own idea of what its address is. And very occasionally, you'll buy a chip that has a built-in address, like say 20, and then you'll want another copy of that chip, which is also 20. And sometimes you can't change the addresses on these things, so sometimes it's not quite as simple as it would otherwise. But that problem doesn't usually come up with the bus pirate, because again, you're only going to have one thing connected to it, because you're playing around. So, it also has this interesting concept of transactions. So whereas in SPI basically just says, here's a serial interface for transmitting bytes forwards and backwards, do with it what you like, and everyone can have various ideas. I2C has a transaction layer built into the protocol, where you send an address and then you say, I want to read something from you, or write something. And I'll show that on the diagram next. There's a little bit more subtle to it, but it has just two lines to it, the serial clock and the serial data. And this arrow here, this backwards forwards thing, single-handedly is the cause of most of the complication in fancy circuits that do this. Because I2C has this wire that goes both ways at various times, depending on what you're doing at the time. And that gets really annoying if you've got one 5-volt chip and one 3-volt chip. Because you can't, so you have to put this fancy little chip in the middle to get them to translate. It gets really annoying. But, yeah. So this is what I2C looks like on the wire. Slightly simpler. I should probably put some colours in to show that it's a bit more subtle than this. Once again, it's synchronous. You have the clock line here sent from the master. And it has this fancy little handshaking signal where it wiggles the lines in the right way to say, I'm going to start now. So you have this proper signal to say, start. So everyone knows what's happening. And then the master writes out this first byte. And the first byte is always the address of the thing you're talking to. And the device might acknowledge or it might not. And then the master, for example, if it's a read, the master will now stop talking at this point, and it will effectively hand over control of the data line to the slave that it's talking to, and then it will still send out a clock to see, dear slave, have you actually replied? And if there was a slave there, it might actually send a reply. And if any of you have particularly keen knowledge, you will know there are actually 9 clocks here. Because what it does is, the master will send out its first 8 clock pulses and its first byte here to say who it's talking to. And then there's an extra little 9th bit at the end, where if there was a slave, it might reply. So here in particular, there's a slave, and it has replied because the line is still being called down. If there was no slave to talk to, that would just float. It would be up here, so the slave would know to talk to it. And again, for every byte that gets transferred, the person at the other end gets a single bit at the end here to say, was that okay? So this one was okay. And this one over here, decided to let go of the line because for some reason it's finished, it's had enough. At which point we stop. So there's this kind of slightly more complex, weird protocol going on, where you have starts and stops and the ands and that. You can send read writes and write bytes, all the complicated stuff. So it starts to get tricky if you're going to type it all onto that little text interface, when you're just trying to talk to a temperature sensor or something. You just say, I want to read the temperature, don't complicate me with all these fancy details. And then finally, just for completeness here, I'll talk about UART, which is yet another exciting acronym that stands for Universal Asynchronous Receive Transmitter, which again is almost meaningless. But the key word in there is asynchronous. I mean, most people just call it serial port. The key word is asynchronous because it doesn't have a clock. It's also symmetric in that you just have 2 ends that talk to each other, or maybe just one end. Maybe you actually only wire up one of you because you don't need to do anything else. You have 2 wires which are called RX and TX. It's all a bit like this on the wire, so there's no clock at all. We just send these bits, and we just have to hope that the person at the other end is timing them in about the same rate that we're sending them. So if anyone's ever tried using a serial console on a machine, you know you have to set the baud rate correctly, because if you don't, they'll just get jumped. Well, this is why. It's because there is no clock line here. You just have to hope that the other side is ticking at the same rate. So you send your byte here. Also, I have no idea why, but for some reason, all of the UART serial protocols tend to put the least significant bit first, but everyone else put the most significant. So I just tried to represent that here by crossing these arrows over just to, it's a random, I don't know why. But, so here's a sort of typical example. We transmit this thing, and maybe at some point later you might receive a byte here. And again, it's literally a single wire. You just hope the timing is right. So that's a sort of a brief overview to the hardware and what it does. Don't worry if you didn't remember or understand any of that. Here's what it is. It's kind of complex. That's what the device is supposed to be there to implement. So using this thing from Perl. So obviously you're supposed to connect to a PC. It's intended primarily for talking to people, as I said on that console. But it does have a binary I/O mode, where you can tell it switch into binary mode, and we will talk more efficiently from the computer to the bus pirate to make it do things, so we don't have to parse all the text. That's always good. It does come with some example Perl scripts that they've written, and they are all terrible. As you can probably imagine, anyone who isn't a Perl expert trying to write simple, nice examples for other people to read. So I looked at these examples, and I thought, yeah, they're annoying. I want to write a better one. So I wrote a CPAN module called Bus Pirate. Very exciting, obvious name. So yeah, there is a secret CPAN module. That tracks away all of the communication with the Bus Pirate. So rather than all of their example scripts, where every single script, they open the serial port, they set the serial lines, and then they send some bytes, and they read some bytes, and they have to know that these bytes in this particular order mean this thing, blah, 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 blah. Throw that all away. Have this abstracted interface, because that's what we like, right? So the module apparently understands bit bang and GPIO, understands SPI, recently understands I2C because I added that, which I had to do. Doesn't understand the other bits yet, which I'll happily talk about them. But I'll maybe add them at some point if I have need for them. And so based on futures, so it fully supports being asynchronous. The very first version I wrote didn't use futures, and so it was synchronous only. And then I thought, yeah, I really should actually do this whole future thing, actually. And I sort of rewrote it, and I discovered actually it's that same number of lines of code, and it's no more complicated or weird, but suddenly it's called async. So sometime I might turn that into a separate talk. Here's an example of how you can use futures to make things work with asynchronous. Topic for a different day. So, how you actually talk to this thing. So, you have the main device bus pirate object is basically just a factory of these mode instances. You want to switch it into some particular mode or some kind of chip, so it's a mode object. It looks like that. So you create your object, your bus pirate, you create your, in this case, bit banging IO object, and that's kind of it. There's no complex opening the serial port, sending bytes, reading bytes, whatever. Abstracts it all away from you nicely. I said it uses futures. So what that means is that every method actually just returns a future object. And in a normal synchronous program, if you don't care about doing async futures and whatever, you have to put this get call onto the future itself that makes it wait and returns the actual thing. So all of these slides are going to have these little trailing get. These little trailing get calls. These are trailing get calls. I use these things so much, I practically don't see the gets anymore, because they just sort of happen. But that's basically what it is. You can largely ignore that. That's all that means. But it does mean the whole thing will fully work with everything asynchronous. So, as an example of a bit banging thing, here's a piece of code. So, we get the bit bang mode object, and we change this to a while loop, where we're just going to toggle this to the bit flag, and we're going to tell it to write that bit out of the miso line. I'm sure that's a bug, that should be masked out. See what they said? The whole miso MOSI concept, they kind of messed that up. So yeah, that should say MOSI there. Never mind. So for example, if we had an LED attached to the board, it would just be blinking once a second like that. We just keep blinking until we stop the program. So it's a very, very nice, simple example where nothing weird and complicated that you have to understand about the device. You can just straight away write this tiny little program, see a blinking LED, and go, wow, I've been an LED blink. That's awesome. I can go on and build complicated things now. And me being me, I decided to write a little ticket application to so here we have, this is the front end. I think this is a little more friendly than typing the command straight into Zero console to wiggle the lines up and down. Because all of these are buttons, and you can just click the buttons and tell it whether to be on or off. And currently all the buttons, all of those lines are in read mode, and when they're in read mode, one of these lights will flash to tell you whether it's currently reading high or low. There's a power control there, so you can turn the power on or off. And I set them all in the colours of the standard probe cable, because then it's nice. You can look at it and you see, oh, it's the orange wire. Where's my orange wire connected? And you can just, it's a bit nicer than the terminal thing. So that's that. There's also a little SPI thing, which works in a much similar, exciting way. The SPI object. And you say, so SPI, as I said, you simultaneously are wiggling the clock line, writing a byte out, probably reading a byte in. So that's all that happens down the SPI wire. So it's kind of up to you to decide, am I expecting to send some data now, and probably ignoring what I read, or am I basically just writing zeros and reading something in? So there's just this simple method called write read that sends a byte, reads a byte, to multiple bytes. The little underscore CS there just means this method will even handle setting the chip select point. So all you have to do is call this one method, and it drops the CS line, writes you out all the bytes, reads in all the bytes, and then returns the bytes that it read. So one single method called here does all that I/O for you. So in this particular example, all we're doing is we're outputting an increasing count of numbers. So maybe you had a little box of LEDs attached to this, so we just start counting LEDs. I did bring one, but it's about this big, so you probably won't be able to see it from the back there. You could have a play with it later, there's nothing particularly exciting. Yeah, all that does is just write out these. And here's an example of reading. So, again, very similar, we call write read. And we don't really have anything exciting to write, so we'll just write zeros out. Because you have to be writing something because you're toggling the clock line, but maybe the thing you're connected to doesn't care. Maybe the thing you're connected to literally isn't going to read because it's something that only ever writes, because maybe it's a sensor. So maybe it doesn't matter, maybe it does. But here we're just going to write some zeros, and this time we're going to capture what comes back in, and we're going to print it. So this is a nice little example that reads into sensor buttons that I've got on a different board. Once a second, it just tells you these buttons are pressed and whatever. And then in I2C you can do largely similar. So another example that looks shockingly similar to the first one. This time with a method called send. So I said I2C has device addresses. So each device has an address. So for example, here we're going to send some data to a chip on address 20. And there's the data we've sent. So again, we're sort of sending these ticks. And again, we can read from them as well. So reads in SPI are a bit interesting because what you do is you write to start with and you say, hi, device with number 20, I want to read from you. And then you shut up for a minute and you wait and see how much it's going to send to you. So the direct read method here takes the address that you want to talk to, and you tell it how many bytes you want to read, because you just keep reading bytes until it's lots. So here's an input. So again, no compressor. But still kind of low level, because most devices you're going to want to talk to, you're not innately going to decide, oh, I need to write a command with these bytes down in. You want to do something even higher level. If you've got a LCD display attached, you just say, I want to write the string here on the screen, or if you've got a temperature sensor, you just say, I want to read the temperature, please. So I wrote a whole new layer on top of device bus pirate, chip. So this one is even nicer. Look at that. That is an entire complete program. I create a connection to the bus pirate. I tell it on my bus pirate I have mounted a chip which is made by, I don't know who makes it, but the chip is called ENA 219, and that's the name on the chip, which happens to be a voltage and current sensor. So I say, here, Mr. Bus Pirate, you've got this chip attached to it. He goes, oh, okay, fine. And now I want to read the shunt voltage register of the thing. And he goes, yeah, okay, here's the number. So you can use this program. You don't have to know anything about how it works internally. You just say, yeah, that's the chip I've got. Read that thing off it, please. Okay, here it is. So I'll go through a few more examples of those in a bit. But that was ultimately what I was trying to aim at, because trying to perform this operation by opening the text console and manually typing things in, you have to do, I think it's either 6 or 7 commands over the serial console to get it that far. And that leaves the voltage once. And then of course it just writes out a raw hex number, and you have to think to yourself, right, well these bits are this field, and that bit's that field, and I have to multiply that by 4, but 2 if that register was there. It's horrible. So this abstracts the whole thing away, makes it very nice. So what things have I actually built with it? There's lots of exciting photos. This is the shiny human interesting bit, rather than the crazy geeky techy stuff. So, as a slight aside, I didn't build this, but this is a kind of cool thing you can do with a bus pirate. Probably a lot of people today will be talking about the Arduino boards, of which I have one somewhere in the other box. They all use chips like that now. These chips that are in no way named after the people who made them. They just happen to be called AVR, even though they were made by people whose initials were AVR. Officially, that wasn't so. These are all these microcontrollers. They all talk SPI to actually program them. So they have this thing called in-circuit serial programming, which means you don't have to take the chip out of the board and put it in a separate programmer and then put it back. You can just talk to the thing while it's on the board and actually program it. So that's how you reprogram it in circuit to update it, develop it, do whatever it's doing with it. It's one of the reasons why, as I said, the MISO and MOSI names are slightly complex, because normally the microcontroller is being an SPI master. So it's doing all this I/O, talking to the chips on the board. But if you're programming it, it suddenly becomes the slave. And so you kind of connect the same pins with the same names, but suddenly the sense of the data is kind of going backwards, and it's kind of breaks your head a little bit sometimes. But anyway, so you have this in-circuit serial programming. And because the bus pirate can talk SPI, you can use the bus pirate to talk to these AVR chips, which is supported by the standard AVR programming program called AVR. So it sort of looks like this. So you just say AVR dude, and I'm using a bus pirate programmer, and you put all the usual AVR dude argument on like there. And this is a photo of me last week. This thing here is my actual AVR programmer, which is a thing that's a lot nicer than trying to use the bus pirate for it. It does things faster, better, natively, whatever. But the AVR programmer itself is an AVR chip. And they release new firmware for every so often, and you can update it. But how do you program the AVR programmer if it's an AVR programmer? You need another one. Oh no, you don't. You just connect it to your bus pirate. So the bus pirate comes with this fancy little probe cable that's got all these little pin connectors on it. So all you do is you connect the bus pirate directly up to the AVR programmer, and then you talk SPI to the AVR programmer from the bus pirate, and you can reprogram it. So I firmware upgraded my programmer using the bus pirate. So that's nothing I wrote myself. That's just what you do. That's one bad thing to do. Whereas everything else I'm about to talk about, I think so. So one of the first things I had to play around with it. The AVR chips, usually you program them through SPI, and when you're programming these for SPI, you need to knock it into stop what you're doing and accept this program mode. So it has a reset pin, and you pull the reset pin low, and that acts with the chip select line. Talk to it. Which is normally fine if you've got one of the huge, say, 64-pin monster chips. You just have this reset pin and it's all fine. But I'm doing a lot of work with the really, really tiny 8-pin AVR chips. So when you've only got 8 pins, you've got two power pins, and that's 6 remaining. Well, that's really 5 if you need a reset pin to program it. So AVR, in their infinite wisdom, came up with another way to program these things, which they call high voltage serial programming, just to put people off. It's actually 12 volts, which isn't particularly high. But the point is that it's higher than anything else you'll ever see on board. So they came up with this fancy custom way of saying, well, if you put 12 volts into the reset pin, then I'm going to believe that that's a reset and I'm going to shut down the programming mode, even if the pin is just a normal I/O pin. And once you go into high voltage mode, you get access to some fancy little configuration bits on the chip that, for example, you can turn off the normal reset pin ability. So you shut down the reset pin as being a reset pin, and now you've got another I/O pin, which is useful on a device that did have 5 pins, you've now got 6 pins. That makes quite a difference. So, because I'm doing a lot of work with these things, I needed a high voltage serial programmer. You can't just connect the bus pirate directly, because it needs this 12 volt line. The bus pirate can't output 12 volts. So I had to do a little bit of extra circuitry. And dangerous prototypes that people who make the bus pirate decided they like this so much they put me on the front page of their website, like that. That's a screenshot, basically. So this is a screenshot of a web page of dangerous prototypes taking a screenshot of the Meta-CPAN web page, where I pasted in this little table to say, if you want to do this, here's the connections to make onto your chip. So this is a double screenshot. This made it onto their front page. I didn't realise this, but somebody pointed out to me. They said, "Oh, hey, you're on the front page." I said, "Oh, sorry." So they sort of pulled this article up. That was me. There's been a long-running rant on the Dangerous Prototypes forum as to whether or not you can actually use bus pirates to talk high voltage serial. Various opinions were saying yes or no, can you do it, can't you? So I posted and said, yes, I know you can, because I've just done it. Because I did it with. So it looks a little messy, but that's currently the circuit that I have at home doing this. So there's the little tiny 8-pin chip there. There's all these little wire coded, blah blah blah. There's a connector out to the bus pirate you can see in the back. It occurred to me this morning actually, this is a really bad photo because you can't see most of the interesting circuits or the wires in the way, but never mind. But I have my first ever actual PCB design is going to the fab today to build some little boards that are going to be much, much smaller than that to do this from. So possibly in a couple of weeks' time I'll have a nice little fancy PCB that I can actually give people and say, look, if you want to do high voltage programming, just use this thing. So that's how it's alternatively, the board might not work because it's literally the first time I've ever done one. I'll see. I'll update you next year. So anyway, so that's what that does. So all of this is many layers of dependency to get onto the thing that I was actually trying to build. So it took me 37 minutes into the talk. I've got to the actual thrust of the talk. So I do a lot of interesting amateur theatre stuff, and every year we turn up at different venues. And I bring along my cue light system that I made, which is 2 boxes with a button and an LED, or 2 buttons for LEDs, red and green, to say go or stop. And they go on a huge long cable between front of house and backstage. So when backstage are ready, we go to start the next scene, they hit the green button. And when we're ready, we hit the green button, we start. And this works great, up until the time when they don't press the green button, and we panic and we think, oh, what's gone wrong? Last year, we turned up. I've got a 65-metre long cable. We measured the space, it was 63 metres. And we just fit. So I've sort of been thinking, it would be nice to have a fancier system. It'd be nice to have more than 2 channels, because it'd be nice that up front of house we can tell people to open the curtain directly, so have a yellow button or something. So I thought, something radio-based. Because then the actors on stage, because the other thing we were trying to do was have radio-controlled props, or sound effects to go the other way. Because if you have an actor on stage that is going to do something that requires a sound, it's really hard for us lots at front of house to know exactly when they're going to do it to hit the button. Whereas if you can somehow mount a little radio module on the actor who's going to do this thing, and they can subtly press the button to fire it, then they can press the button to fire the sound effect, and it looks so much better, which you need with the radio things. And it turns out you can kind of buy these things if you have the budget for a West End stage show. If you do amateur dramatics, you can't. So I thought, I'm going to build these things, because it sounds like a cool fun project. So I bought these little radio modules, these NRF Yeah, so these by a company called Nordic Semiconductor, they're wonderful. They are, here, yes, they are, you probably can't see it, but they are this big. They cost £1. They talk 2.4 gig. This thing would probably reach the back of the auditorium if it was empty, but I've got a slightly bigger one at home with an aerial on it that they claim will do 100 meters, I think. The datasheet is in Chinese, but I think it means it will do 100 meters. I haven't tried it yet. But, anyway, so these have passive radio modules. They talk SPI, which is quite nice. They need to talk to bus pirate. It does have quite a complex command set, and it did take me 4 weeks of hacking Perl to manage to get the thing to transmit a packet. So they're slightly non-trivial to talk to, because they're very stateful. They have a lot of configuration registers, a huge number of bits that you have to get in the right place, and the datasheet doesn't really point out, but it has a lot of interdependencies where if you set this data rate to a certain low speed, you have to remember to edit the timing parameters over here, otherwise the thing will try to do something while it's in the middle of transmitting a packet and the whole thing will crash. It's very complicated and impossible to do by typing numbers into the serial console. So the reason why I wrote this thing in the first place was to be able to write some actual code. So there's it took me about 5 minutes to bend the cable and make it stick for long enough to take this photo. So I'm sorry that the bus pirate is out of focus, but that's the best I can do. But that's the thing there, mounted up on the bus pirate cable. Talking, you obviously can't see talking radio, but that's what radio is. And so, rather than typing lots and lots of numbers into the serial console, the program looks like this. You enter, you tell it, here's the name of the chip I've got, and you just change config, and you just pass it a little key value list of, here's the config I want. So I want to be in not receive mode. Apparently that's what Nordic thinks is a good idea. I want that data rate, talking to this channel, transmitting to this address. Okay, fine. I want to transmit this packet, please. Go on, do it. And now I'm just going to sit in this while loop waiting for it to tell me either that it sent it or that it ran out of retries and failed. The retry logic, there are no fiddles with these things. That retry logic is the thing that took me a week to work out, because if you change the data rate, the retry time is too short. So it says, oh, I'm going to send a packet now, or I haven't received an acknowledgement yet, even though I'm not finished sending the packet. So I'm going to send it again, and corrupt it on again. And then I'm going to send another, oh no, great. So you have to remember to fiddle those. It's really important. So anyway, so that's what the code looks like. I was tempted to write a slide comparing how you would talk to that straight over the terminal. I couldn't manage to work out how to talk to it on the terminal, because I've literally never done so. But I suspect if I had, this would be about 3 pages worth doing that. And of course, this bit here is pulling the hardware, so I can't type that fast. I can't say, look, is it done yet, is it done yet, is it done yet? So, yeah, this code makes some nice. Yes, but the one slight annoyance is that the thing does have an interrupt pin that tells you it's ready now, but you have to poll it. The bus pirate itself doesn't have any way to do interrupts. And the other problem that I had was that having built this thing with the bus pirate to talk to a radio module, I thought, great, I think it's working. Well, how do I know it's working? Well, I'm going to need another one. I need a bus pirate. No, I'm not. I'm going to make a bus pirate. So I wrote myself a bus pirate hack that is my own design. I only talk to binary because I'm just trying to talk to it from the Perl script. I don't care about the terminal at all. And I spent a very long time coming up with a silly cute name. So it's called a maverick because it's based on an AVR. And the word maverick, there are no words that have the letters AVR in the middle. So I had to look for a word that had another letter. And I stumbled upon maverick. And I thought, well, pirates are kind of a bit mavericky. So I'm currently calling it the Maverick. And I don't have a photo of it. It doesn't look very exciting. It's an Arduino Nano sat on the board with not a while. But that's kind of what it is. And so I'm slowly working it out into a design which I shall build and publish at some point, because I want to put in a bunch of extra things. So earlier on I mentioned this fancy sensor, the E219. The voltage current sensor module. I talked about I2C. I'm tempted to put one of those on the Maverick because the bus pirate itself will supply power to the circuit that you've got plugged in. I very nearly melted my bus pirate and the chip because I miswired it. And if the bus pirate had a current sensor and a voltage sensor, it would have been able to tell me like that. It probably won't look exactly like that because that is. I got bored one day and fiddled around with the ticket 7-segment display.
So that 4,000 volts.
No, you see,
4.9.
yes, you see, yeah. Tom Aldworth pointed out to me. I probably want to make the decimal point a bit bigger there, because yes, it's not 4 kilovolts. It's 4.9. And most crucially, it can tell you the current that you're drawing. So 4.6 milliamps. That's it attached to a single LED drawing. And that's good. And so it would be nice if I had a piece of hardware that could tell me this is how much current you're drawing, and monitor it and say, it's hit too much, shut down please. So I want to put one of those on. And so I thought to myself, well, if I've got a current and voltage sensor, I'm going to want a display. So there's these fancy chips by Natsu called 7219s that near little LED drivers. They talk SPI. Ooh, SPI, that sounds like a thing I talk to with the pirate. I'm going to put one of these on Maverick as well, because they look like that. It's a really cute little thing. So this is again my bus pirate talking to this LED module. That's a clock. That's just a fan time. That was a piece of code I wrote literally in 10 minutes. The thing came in the door, I thought, oh, my LED's here. What how long will it take me? I unwrapped it. I started writing code. 10 minutes later, I had that. It took me another day to finish writing the documentation, but it's CPAM, but never mind. So, in summary, a bus pirate. It's very useful for talking to fancy little bits of electronics hardware, as I'm sure you'll see many more of today from the computer. It's very easy to program from Perl, because you can use device bus pirate. And I'm sort of starting to carve out this namespace on the CPAN, device bus pirate chip. That's how you pronounce that. So there are thousands of I2C and SPI devices in the world. I'm hoping and expecting that people will start playing around with these things and writing more of them. There'll be a nice library of these things, so that you can just say, oh, here's a random chip, I will talk to the bus pirate from Perl, and it will just work. That's it. Any questions? Oh, one already.
Most importantly,
yes.
Who are you using prefab?
Osh Park at the moment, because they're the only people I can find who will do boards and runs of 3.
Yeah, I want to run 10 and not have to pay hundreds and hundreds.
Oh, they're not, they're really cheap. I keep talking to people who are, so there's somebody at work who has invested a fortune in doing his own copper etching at home, and he does single layer boards. So I explained to him, Osh Park are going to build me 3 2-layer boards with solder resist and silk screening on both sides for £15 for the lot, and they will post them to my house for £15. So I don't know how they're doing this. I'm not going to inquire. As long as it arrives and works, I'm happy. But yeah, these things are not anywhere near as expensive. Yeah.
Well, is that full size PCB or that size?
Oh, so the one I'm doing is this big. It's Dangerous Prototypes came up with a very bizarrely named but very nice idea called Sick of Beige, because they said they were sick of beige boxes. I don't know why the name, but the idea is that they have a bunch of standard-sized board footprints that if your board roughly fits about this size, fit it into this standard size, and it puts the mounting holes and everything in the right place, so you can buy a case from them that exactly fits it. And they also publish these 3D printing designs for how to build these things. So they're trying to build this community of standard-sized boards in standard-sized boxes. So I'll see how that works. Another one?
You're doing some polling on those slides.
Yes, I am, because the bus pirate itself doesn't have interrupts.
So since you're using the asynchronous backend for your module,
Yeah.
do you have like a callback kind of syntax instead of pack it away in the module, the polling?
Yeah, I could, but the problem is that the polling, it's a very high-level thing, because I'm basically polling, asking this one register, and then testing whether either of these bits are set. That's a very high-level thing that you can't really do at such a low level.
Yeah, besides there are features, so you can just put one timer in your loop. And
I mean, I could potentially say, here's a piece of code, just call it repeatedly until it's true, and then yeah, we're nearly out of time, but maybe one more.
Yeah, question two. Why don't you use the voltage sensor on the bus pirate?
You can't talk to it in binary mode.
Oh,
This thing is intended for people to talk to on tech. There are so many things that you can do in terminal mode that you cannot do in binary I/O mode.
that sucks.
The main reason being that they ran out of space on the flash to program it in. They have to start making compromises. So they decided binary I/O, not the primary target, we'll start throwing. Whereas the whole point of my Maverick is to do binary only, so I can do all that fancy stuff. Doesn't look like there's any more questions. I think we just go on.
One more question actually. Why, since this is a module and it's all abstracted and stuff like this, why aren't we talking to the bus pirate in text mode?
Because I really don't like doing silly parsing. And also a lot of the I/O, because it's intended for humans to read, it prints out a long string of text.
Right.
Well, that takes a long time to send over the serial line. Whereas the binary I/O mode is just single bytes here and there. It's just faster. Go on.
Does the binary mode support the macro so you can do I2C sniffing?
No. Oh, it's got certain sniffing things. But so in text mode, they basically built a basic scripting engine. So in text mode, you can send an entire basic script and have the thing do stuff. But again, in binary mode, there's nothing like that.
It's the
very raw right now.
sniffing mode is really, really useful.
I have a proper Salier clone, which is much nicer for doing all of that sniffing. So I don't use the bus pirate for sniffing. I have the real thinking. Anyway, I think we're over time now. So I think I better.
Got a couple more minutes.
You can put me. Oh, okay.
I was just kind of stop talking and ask a question.
All the questions are coming from this area. So never you there. Everyone asleep maybe. Hello.
Do you, so you're talking to the RF chip from Perl?
Yes.
Does that mean you're running it off like something bigger than a NAT, or are you running like a laptop or a Pi both at one end?
Well, so again, the bus pirate is think of the bus pirate more like Devo Rebel for hardware. You wouldn't run a real program for production use from Devo Rebel, but it's great for playing around with new ideas.
Did you rewrite that same code for
The actual chips. Yes, I mean, so specifically the NRF chips, there are some interesting Arduino or just plain AVR libraries that people have written. Yeah, that you can talk to, fine, yeah. And so I do those, I run those, I mean, on my tiny chip I actually wrote the code custom because I needed it very small, very custom. But yeah, you can just get these things for the real hardware. It's just playing around with it from the computer. Because obviously if you've got radio modules, you need two of them working to know, is the thing working at all? Whereas things like LEDs, you can look at it and say, oh, look, that way. That's fine. I guess that's... Oh, no, one up there.
You said multiplier only supports certain features in binary mode. Is
Yeah.
it possible to reprogram it and say re-import some features in text mode?
It is to an extent. So one of the reasons I'm building the Maverick on AVR is because Atmel are very nice and open with these things. You get, built by Atmel, the AVR GCC, which is just built GCC for the AVRs. AVR do free software. You can buy these burners for like £3. So for £3 and some open source software, you can develop for AVR chips. The Bus Pirate has a PIC on it. I don't like PIC. PIC is almost the diametric opposite. If you want to write anything for a PIC, you download a 200 meg Windows executable and you run it on your Windows machine and you plug it into the machine, into the chip with a programmer that costs maybe 30 or 40 quid. It's very weird custom hardware. And just kind of hope that it works. So technically it's an open design, but in practice, if you want to play around with it and modify the Bus Pirate, you need to run Windows and download their software and work within their space. So I kind of dislike that. There are custom firmwares. Probably there are people doing weird binary I/O things. They're kind of hard to find because it's very hard to bootstrap yourself into that environment if you're not already there. Yeah, I think we'll stop there. People coming in. So thank you very much.